So this is 12.2, and we're going to go over independent and dependent events. So our objectives today are to determine whether an event's independent or dependent and define the probability. These are our vocabulary. So an event is independent if the occurrence of one event doesn't affect the probability of the other. So an example of this is when we toss a coin twice. If we land on heads up the first toss and we land on heads up on the second toss, then these are independent events, because if I toss it the first time I get heads, it doesn't affect what I get the second time. So the outcome of one toss doesn't affect the probability of the heads or on the other toss. So to find the probability of tossing heads twice, you multiply the individual probabilities. So in other words, if I tossed it the first time I got heads, that was a 1/2 percentage or probability. And then again, when I toss it the second time, I still have a 1/2 probability. So when I multiply that 1/2 times that 1/2. So when we talk about independent events, it's when what happens first does not affect what happens second. So if A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B. Now this is found on your formula sheet, but what I would really like you guys to do is write the word and when you see the word and, you're always going to multiply. Sometimes you won't see the word and, you'll be able to imply that there's an and in the problem. Okay, so right here, a 6-sided cube is labeled with the numbers 1, 2, 2, 3, 3, and 3. And then 4 sides are colored red, 1 side is white, and 1 side is yellow. It says find the probability. So what I'm going to do first is I'm going to go through each of these. So first of all, if it's a 6-sided cube and only one of the sides has a 1, I'm going to write 1 right here, then that means that my probability is 1/6 of getting a 1. Then if I was looking at the 2, now I have 2 on 2 of the sides. So that's going to be 2/6, which reduces to be 1/3. And then we have 3. I'm going to write the word 3 again. And this one appears 3 times. So that's 3/6, and that's 1/2. Now let's talk about these colors. So with the colors, we have red, and it says that 4 of the sides are red. So again, that's 4/6. That reduces to be 2/3. Then we have 1 is white. So white is 1/6. And 1 is yellow. So yellow is again 1/6. Okay, so this problem says, what is the probability that I toss a 2 and then another 2? So up there at the top, I see that we have 1/3. So that means I'm going to multiply 1/3. That would be my first tossing of a 2. And then I have 2 again, and I'm going to have 1. So it's going to be tossing 2 once does not affect the probability of tossing 2 again. So the events are independent. So I have probability of 2 and then 2. So I multiply the probability of 2 times the probability of 2. So that's going to give me 1/3 times 1/3. Now the other one is tossing a red, then a white, then a yellow. And if you remember, when we did red, it was 2/3. White was 1/6, and so was yellow. So here again, we're going to multiply those 3 probabilities together. The result of any toss does not affect the probability of any other outcome. So here again, we're going to multiply the red times the white times the yellow. So that's going to give us 4/6 times 1/6 times 1/6. Now notice I put 2/3 here. It doesn't change the outcome in the end. You can reduce it before or after. It doesn't really matter. So your result is 4/216 if I didn't reduce it, and that would be 1/54. If you did reduce it, it would have been 2/108, and so that still reduces to be 1/54. So then it says, what's the probability of rolling a 6 on one number cube and a 6 on another number cube? So again, these are independent. They didn't affect one another. So rolling a 6 on one number cube is 1/6. Rolling a 6 on the other number cube is also 1/6. So we're going to again multiply the probability of a 6 and a probability of a 6. So that's going to be 1/6 times 1/6, which is 1/36. Now, part B down here says tossing heads, then tossing heads, then tossing tails. Well, the probability of tossing heads is 1/2. The probability of tossing heads again is 1/2. And then the probability of tossing a tails is 1/2. So we're just going to multiply those 3 1/2s to each other. 1/2 times 1/2 times 1/2. And recall that we multiply across the top. 1 times 1 times 1 equals 1. 2 times 2 is 4, times another 2 is 8. Okay, now let's talk about dependent events. If the occurrence of one event affects the probability of the other, for example, suppose there are 2 lemons and 1 lime in a bag. If you pull out 2 pieces of fruit, the probabilities change depending on the outcome of the first. So let's talk about how this works. So if we have 3 pieces of fruit in the bag, and we have 2 lemons and 1 lime, so the probability of me pulling out a lemon the first time would be 2/3. The probability of me pulling out a lime the first time would be 1/3. Now, the question is, what would be the probability if I pull out a lemon and then another lemon? So that would be 2/3 times 1/2. If I pulled out a lemon and then a lime, that would be 2/3 times 1/2 as well. Now, if I pulled a lime out first and then a lemon, well, if I pull a lime out, there's only lemons left in the bag. So that would be 1/3 times 1. And I can't pull out another lime if I pulled out a lemon, or if I pulled out a lime, because I don't have any limes left in the bag. So the probability of a specified event can be found by multiplying the probabilities on the branches that make up the event. For example, the probability of drawing 2 lemons is 2/3 times 1/2. That equals 1/3. Because again, we multiply across the top, that's 2, and this is 6. 2/6 is reduced to 1/3. So to find the probability of dependent events, you can use conditional probability. That means, what is the probability of A given that B has occurred? The probability of event B given that event A has occurred. So if A and B are dependent events, then the probability of A and B is equal to the probability of A given that the probability of B has occurred. So let's talk about how this works. So 2 number cubes are rolled. One is white and one is yellow. We're going to talk about why these are dependent in just a second, but it says then find the indicated probability. The yellow cube shows a 6. So that means one of my cubes has a 6. And so my only combinations, if one of the cubes shows a 6, is 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6, because the first one has a 6 on it, and then the only other choices for the other cube are 1, 2, 3, 4, 5, and 6. So when we do this, we can see that those are 6 numbers, and when we roll 2 cubes, we have the potential outcome of 36. That's the maximum that we can have. So we're going to have 6 over 36. Now, of those 6 over 36, again, let's look at what they were. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. I'll put some commas here so y'all don't think these are actually numbers, okay? So then it asks us, we also want, of those 6, how many of those have a sum that's greater than 9? So not including 9, but greater than 9. So when I look at this, 6 plus 4, sum means addition, is 10. 6 plus 5 is 11. 6 plus 6 is 12. So I then, of those 6, I'm going to take 3 of them. So now what I'm going to do with these 2 separate probabilities is I'm going to multiply them by each other. So I'm going to multiply the 1/6 up here times the 1/2 here. So when I do that, I'm going to get 1/12. Now, I want to bring something to your attention back here. Notice that this 6 here matches this 6 up here. So whatever was in the denominator, or actually the 6 right here, whatever was in the denominator here, or in the numerator here, becomes the denominator down here. Let's look at another one just to illustrate that for you a little bit more. Okay, so we have 2 number cubes again. One is white and one is yellow. Explain why the events are dependent, then find the indicated probability. So we got a yellow cube that shows an even number, and the sum is 5. So let's look at yellow cube with an even number. So what are my even numbers? So I could have 2, 4, or 6. So then I would have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, or 2, 6. And so on down here. So this would be 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. Down here, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So again, our total potential outcomes were 36. And if you count these up, we got 3 rows, 6 columns, so that's 18. So that's going to be 18 over 36 outcomes. And let me write this down here so it's not so confusing. So just so we don't get confused. So this is going to be 18 over 36, which we all know reduces to be 1/2. Okay. Then the second part of this problem says the sum is 5. So we want to look at now these 18 numbers. So we're going to put our 18 down here as our denominator again. If it was our numerator in the top, it's going to become our denominator in the second one. So of the 18, how many of them have a sum of 5? So if I look at the first row up here, I see 2 and 3. That's a sum of 5. If I look at the second row, I got 4 and 1. I don't see anything in the third row. So that's only going to be 2 out of the 18. So that's 2 over 18, which reduces to be 1 over, 9. 1 over 9. Okay, now again, we are going to multiply these two fractions together. So that's going to be 1/2 times 1/9, which is equal to 1 over 18. So go ahead and do this, check it out, and then come back to me. So this says 2 number cubes are rolled, 1 red, 1 blue. Explain why the events are dependent, and then find the indicated probability. We haven't really talked about why it's dependent. It's dependent because one of the cubes is fixed, and the other one, the outcome of the second one depends on the first one. So the red cube shows a number greater than 4. So what are the numbers that are greater than 4 on a number cube that's got 6 numbers on it? That would be 5 and 6. And so then we're going to look at the sum is greater than 9. So here again, let's do it this way. I'm trying to figure out a way. Let's just fit it up here. So we've got 4 and 5. Okay, so we've got again 4, 1, 2, 3, 4, 5, 6. So 4, 1, 4, 2, 4, 3, 4. No, sorry, greater than 4. My bad. So it's going to be 5 and 6. So it's 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. And then 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So those are the numbers that are greater than 4. So we have 12 of those. So that's going to be 12 over 36. So that's going to be 1/3. Then the next part of the problem says we want a sum that's greater than 9. So let's look at these numbers and see where we can come up with a sum that's greater than 9. So here I've got 5 plus 5, that's 10. 5 plus 6, 11. 6 plus 4 is 10. 6 plus 5, 11. 6 plus 6, 12. So that is 5. And again, remember, we're going to take what our numerator was up here, 12, and we're going to put the 5 over it. So now what we do with these two numbers is we multiply them by each other. 1/3 times 5/12 is, multiply across the top, 1 times 5 is 5. 3 times 12 is 36. So that's our answer. So conditional probability often applies when data falls into categories. So in many cases involving random selection, events are independent and there's replacement, and dependent when there's not replacement. So when we look at a standard deck of cards, we have 4 suits of 13. We have face cards, and we call those jacks, queens, and kings. So your guys are going to have to really know a deck of cards to be able to be successful in this unit and on the EOC and on a quiz or test. So we have spades up here, and diamonds, and clubs, and hearts. We have half the cards, which would be 26 of them because there's 52 cards in a deck. So half of them are red, half of them are black. And then we have 1 of each card. So we have 4 of each card. So we have 4 aces, 4 sevens, 4 jacks. So we're going to use those types of things that we know about a deck of cards to then work a couple problems. So this one says selecting 2 hearts when the first card is replaced. So the key word in this problem is replaced. So if it says that it's replaced, then we know this is independent. So that's the first thing we want to look at. So this is an independent problem. So if we have hearts, there are 13 hearts in a deck of 52 cards. Now it says we replace it and we select another heart. So this is not going to change. It's going to be 13 over 52 times 13 over 52 because again, we replace the card. So when we do 13 over 52 times 13 over 52, and we put that in our calculator, we're going to get 1 over 16. And remember, when you multiply the 13 times the 13 and the 52 times the 52, divide the 13 over the 13 times 13, which would have been 169, over 52 squared. And whatever you get, you can then push math in 1 and get it to reduce that fraction. All right, so on the second one here, it says selecting 2 hearts when the first card is not replaced. So now this time it is dependent. And it's dependent because we did not replace the card. So this time we're going to pull a heart. So that would still be 13 over 52, but then we're not putting the heart back. So now we only have 12 hearts left. We only have 12 hearts left and we only have 51 cards left. So not replacing the first card means that there will be fewer cards to choose from. So affects the probability of the second selection. So the events are dependent. So we have 13 over 52 times 12 over 51. And again, when we do that in our calculator and reduce it, it's going to be a 1 over 17. And please don't forget to reduce these when you guys do a quiz or a test. All right, a queen is drawn, not replaced, and then a king is drawn. So again, because that word not replaced is there, we know that this is dependent. So not replacing the first card means there'll be a fewer cards to choose from, affecting the probability of the second. So the events are again dependent. So the probability of a queen is 4 over 52 because there are 4 queens in the deck. Now the probability of the king is 4. Now again, we didn't replace that queen, so we only have 51 cards left. So we're going to do 4 over 52 times 4 over 51. When we do that and reduce it, it's going to be 4 over 663. Okay, so on this next set of problems, go ahead and do this and then come back to me. So it says here a bag contains 10 beads, 2 black, 3 white, and 5 red. Beads are selected at random to determine whether these are independent or dependent. And okay, so it says selecting a white bead, replacing it, and then selecting a red bead. So my question first is this dependent or independent? If we replace it, it's independent. So how many white beads were there and how many red beads were there? So replacing the white bead again means that it's independent. So we're going to find the white beads, that's 3, and we're going to put that over our total beads. In the red, that was 5. Going to put that over our total beads, that's 10. Multiply across the top, 3 times 5 is 15, 10 times 10 is 100, and that can be reduced because both of them are divisible by 5. So our actual final answer here is 3 over 20. Okay, this next one, selecting a white bead, not replacing it, and then selecting a red bead. So this time our beads are going to decrease. So again, we still have the same number of white beads. So if we're not replacing it, though, it's going to be dependent. So we've got, again, our 3 over 10, but this time we only have 9 beads left in the bag. So we got our 5 over 9. 3 times 5 is 15, 10 times 9 is 90, and 15 goes into 96 times. So this reduces to be 1/6. Okay, here's our last problem. Selecting 3 non-red beads without replacement. So here we have 5 beads that are not red, and we have 10 total beads. But every time we take one out, the non-red beads decrease and the total decrease. So this is definitely going to be dependent, and we're going to actually multiply. So we had our non-red beads, so we had 5 over 10, and then both of those numbers on the top and the bottom decrease. So that's going to be 4 over 9, and then it's going to be 3 over 8. Again, multiply across the top. 5 times 4 is 20, times 3 is 60. 10 times 9 is 90, times 8 is 720. 60 goes into 720 12 times, so that reduces to be 1/12.